Oops, sorry guys. Camera's falling off here. There we go. So let's continue on with some stoichiometry. We have now finally working our way to the longer equations. And I don't know if you noticed, but in the SOL, more of the stoichiometry work were these little relationships where you were relating grams to moles, moles to grams, moles to liters, molecules to moles. There wasn't a lot of the bigger questions. Let's do real quick before we move on to a bigger question. Let's do another one of the shorter questions. For example, letter C above here, we have 2.4 times 10 to the 24 molecules of diatomic nitrogen into liters. So, diatomic nitrogen, right? So the first thing we have to do is our given, and then this area is how are we going to make molecules into moles? So we have to divide molecules by something. We're going to divide it by Avogadro's number. So that is molecules per mole. If you are like me and you really don't want to use the scientific notation, one thing you can do is 10 to the 24 and 10 to the 23. They almost cancel out. So if I do that, I can get rid of 23 out of the 24 tens and 23 out of the 23 tens. So I end up with 2.4 times 10 and over 6.022. If that doesn't make sense, make sure when you do the math with scientific notation that you put brackets in. So 2.4 times 10 is 24 divided by 6.022. That gives me, that answer would be 3.985 moles if I was done. I'm not done yet though because my answer I wanted in liters. So we're assuming this is a gas at STP. So that means this would have to be up here. We're going to put whatever is going to convert our moles to liters. And so 1 mole is 22.4 liters. So 3.985 moles times 22.4 gives me 89.27 and some change. But if we look back at our answer, we only have 2 sig figs, so we only want to give 2 sig figs. Let's just say 89 liters. Right, here's another one-shot or two-step example. We have 4.5 grams H2O, and I'm gas. That's what the G means, gas. And let's convert that into liters. Okay, grams to moles. So this column is getting our grams to moles. So if we have grams and we want moles, we're going to put in here our molar mass. So molar mass of H2O. So H is 1, and there's 2 of them, so 2 plus 16, 18 grams per mole for H2O. So if I just did 4.5 divided by 18, that would tell me that's 0.25 moles. Okay. But we want to actually make it into liters, so once again, assuming we're at STP, 22.4 liters times the 0.25 moles that I have. So multiply by 22.4, I get 5.6 liters. So going back, we'll put it, and that's 2 sig figs already, so we're good. So I hope those one steps make sense. If they don't, please go back and review the previous video. We are now going to move on to the more complicated ones where we have the formula. And most of the ones I saw on the SOL with formulas were mole-to-mole ratios. And so let's start. The first thing to do in mole-to-mole ratio is you have to balance the equation. And this one looks pretty complicated because of the way it's arranged. But think about the S2O3. That's an ion. See, there it is. It's an ion. Let's see. We have 2 sodiums. 4 sodium. So that's a problem. So we can put 2 here. Let's see what that does. S2O3. There's 1 S2O3 there. There's 2 S2O3s here. 1 Ag, 1 Ag, 1 Br, 1 Br. So we're good by balancing it. And remember, the ones that we didn't put any number in, that's just the imaginary 1. So how many moles of Na2S2O3 are needed to react completely with the silver bromide? Well, excuse me, I'm losing my voice. With the silver bromide, if we need moles, if we had 1 mole of silver bromide, we'd need 2 moles of sodium. And by the way, S2O3, if you look it up on your polyatomic ion, it's one of the ones we don't deal with very often, and that is thiosulfate. So this would be sodium thiosulfate. And this would be sodium silver thiosulfate. Okay. So we are going to take the mass of silver bromide and check and see how many moles of silver bromide that is. Compare it to the molar ratio of sodium thiosulfate to silver bromide, and then we will be done. So if we go back to our check, notice, remember we do those with 3, and we're going to put our given in here. 42.7 grams silver bromide. And then we need to put something in here that's going to convert grams to moles. And so what do we put? We're going to put molar mass of silver bromide. Pretty straightforward. We're going to get our periodic table. You're going to look up silver. And silver is atomic number 47. It has a mass of 107.8682, and you can round that to 108 if you prefer. I'm going to actually go ahead and do that, 108. And then bromine has atomic number 35, and bromine is 79.9, so I'm going to round that to 80. So 108 for silver plus 80 for bromine gives me 188 for silver bromide for the grams per mole. 188. So 42.7 grams is, if we do 42.7 divided by 188, that would be 0.227-ish moles. Okay. But let's just go ahead and wait. We're going to go ahead and do the next step. So the next step is moles that I want to find out. Moles that I want over moles given, okay, from the equation. So I'm going to go back to my equation. The thing I was given is silver bromide, and the thing that I'm looking for, sodium, 2S2O3, sorry, I know you guys can't read that, Na2S2O3. Well, if I look at my equation, 1 mole of silver bromide, you guys can see that right there, 1 mole silver bromide, corresponds to 2 moles of sodium thiosulfate. Okay, now let's check. We want our answer in moles. The only time I need this blank space is if I need an answer in grams or liters or molecules. If I am looking for moles, that's all I need. So remember, I need this block if I have something other than moles to start with. This is to make my given into moles. And this is to make my moles into my answer. So if my answer is in moles, that's all I have to do. So now, 42.7, we're going to multiply the ones across the top, so 42.7 times 2. And then we're going to divide the ones on the bottom, so divided by 188 and divided by 1. I need 0.45 moles of sodium thiosulfate. Okay, so the next question continues with this same reaction, but I didn't leave much space for you guys, so I'm going to slide my extra paper in here. And we're back at the same reaction, but now we're looking at what is the mass of sodium bromide that will be produced if I started with 42.7 grams of silver bromine. So we really start the exact same way. Right? And same first step. This is exactly the same given. So it's silver bromine, 188 grams per mole. But now in this next part, now I'm no longer looking at the sodium thiosulfate. I'm looking at sodium bromide. That's where I'm wanting to go. What is the mass of sodium bromide? So in this column, I'm going to put the molar ratio where I have moles that I'm looking for over moles that I was given. And once again, going back to the equation, 1 mole of silver bromine, now it exactly equals 1 mole of sodium bromide, excuse me. So let's put the silver bromide here. 1 mole is 1 mole. So that's a molar ratio of 1 to 1. Okay. If I was looking for moles, that would be done. But in this case, what is the mass? So I actually want grams. So I need to put in here something to make my moles into grams, and I need my molar mass of sodium bromide. So sodium is atomic number 11, and it has a mass of 22.9897. I am going to round that to 23. And then I'm going to look for bromine, which is at 35 again, and I'm going to round it to 80. So 23 plus 80 gives me 103 grams per mole. So now I'm going to multiply across the top, and I'm going to divide from the bottom. So 42.7 times 1 times 103 divided by 188 divided by 1. I'm going to get 23.39 grams of sodium bromide, but I'm going to round that to 3 sig figs. 3 sig figs, 42.7. So 23.39 becomes 23.4 grams of sodium bromide. So I'm just going to go ahead and write that in on my sheet. All right, let's do a couple more. We're switching to a different reaction now. By the way, guys, one thing that you can do while you're watching the videos is watch it get started, put it on pause, see if you can solve it, then watch me complete it. Then if you don't get it, then you can rewind it, try it again. That can be a little bit more helpful than just following along. So especially with these multiple steps, look at the problem, pause the video, look at the problem, try to solve it, then check your work. So from the reaction, B2H6, that looks distinctly covalent to me. And why would we say that? Well, boron, it's right there on our dividing line. It's a metalloid, right? One of our metalloids. And H6, hydrogen. Hydrogen's our flexible guy. He can be either. So we could say that is diboron hexahydride, if we name it covalently, diboron hexahydride. And it is reacting with diatomic oxygen. And now it is forming HBO2. BO2 is borate, I believe. It's not one of our more common polyatomics. I believe it's borate. But so we could call this hydrogen borate if it's acting, but it's probably an acid. So what would that be? Boric acid and water. So let's go ahead and balance it. B2 on this side, we only have one B over there, 6 H's, so we've got 3 over here. So let's start by just doubling this before we do anything else. So that fixes our B's, right? And now we have 2 H's plus 2 H's, that's 4 H's, and we have 6 over here. We have 2 oxygens and 2 oxygens, 3 oxygens. Let's try this. Let's try 1, 2 H's, 1, 2 H's. I need 6. So if I make that a 2, H2 times 2, that's 4 hydrogens, plus 2 more hydrogens, that's 6. So now let's see, we have our hydrogens balanced, our borons balanced. Let's check our oxygens. 1, 2, 3, 4, because it's doubled, oxygens plus 2, so that's 6 oxygens. And over here I have 2, so I need to multiply that by 3. So our coefficients would be 1, 3, 2, and 2. All right, so this is a non-standard combustion reaction. I don't know if you guys recognize that, but it tells you that. What volume of O2, so that's what we're looking for, what volume of gas will be needed to burn a mass of the diboron hexahydride. Let's see if we can fit it in here. So I'm going to make my little grid, and I'm going to start by putting my given 36.1 grams B2H6. So over here, let's just go ahead and put in the next thing we need. We know we're going to put our moles from our equation, mole 8 of the O2, since that's what I'm looking for, that's my want to find, over the moles from the equation of my B2H6. So let's go ahead and go to the equation. Mole O2, that was 3. 3 is our coefficient for O2. And B2H6, 1 was my coefficient. So I now have started my problem. The only thing I need to figure out is, do I need to put something in here, and do I need to put something in there? Well, to decide if we need to put something in this lower left-hand corner, I need to say, am I already in moles of my given? And in this case, I have 36.1 grams. So no, I'm not already in moles. I need to be in moles. So the first thing I'm going to do is convert 36.1 grams of B2H6 into moles by putting in my molar mass of B2H6. And if you look at your periodic table, boron has an atomic mass of 10.8 and hydrogen is 1. So I'm going to go ahead and do, I'll just go ahead and round. So boron will do 2 borons at 11 plus 6 hydrogens at 1. So 11 plus 11 plus 6. So the 2 borons, so 22 plus 6 gives me 28 grams per mole. By the way, it is okay to use more decimal points and not to round. Okay, now, last space. I only need to use this if my answer is in something other than moles. My answer is volume. So my volume to mole relationship is what I need to put here. And I know that 22.4 liters, it's 22.4 liters per mole. And so I now have every quadrant filled in. Remember, we don't often need that. So now I can go multiplying across the top, dividing across the bottom. 36.1 times 3 times 22.4. That's across the top. Then let's divide by the bottom, divided by 28, and divided by 1. It's a lot of oxygen liters. And let's see, we need 3 sig figs, so let's do 86.6 liters as my final answer. Okay, back to another same question. How many molecules of water are produced from 19.2 grams of the diboron hexahydrate? All right, so 19.2 grams of B2H6. So if you look up here, we know that when we have grams, we need to put in the molar mass. This is, once again, diboron hexahydrate, so I know it's still 28 grams per mole, so I can do a little quick carry down. That also means that this is still 1 mole, no matter what I'm looking at, 1 mole of B2H6. And I'm looking now, instead of for the oxygen, I'm looking for the water. I'm looking for the H2O. So if we go back up to our equation, we had 1 mole of the diboron hexahydrate, we had 3 moles of the oxygen gas, we had 2 moles of the hydroborate, and then we had 2 moles of the water. So 2 moles water. So if I wanted moles water, I would be done, but now I want molecules. And so now we're going to put in the molecule definition of a mole, or 6.022 times 10 to the 23rd. So multiply across the top, divide at the bottom, 19.2 times 2 times 0.6022 times 10 to the 23rd, divided by 28. So I get 8 1/4 times 10 to the 23rd molecules. Okay, so the next bit is another stoichiometry problem for the combustion of gasoline, and I give you the structure of gasoline, C8H18. I'll even get you started on that, but you guys can balance it, right? So, and we always have carbon dioxide and water. And I'm going to leave this for you to practice on your own. In addition, try writing out your steps for solving a stoichiometry problem. You may want to say, if you're doing a mole to mole, if you're doing a mole to mass, and write it out. And if you need more space, or if you'd like to make yourself a flow chart or something, please by all means do so. The more details you give yourself, the better.